And I'm Vijay Gill. I'm a senior network architect for AOL Global Network Operations. And so in Vegas, we were talking at the NANOG reform meeting that building a 10G backbone was fairly easy. And one of the reasons some of the presentations for NANOG were quote-unquote boring and I believe also quote-unquote lame was the fact that most of the heavy lifting had already been done. And I think Joel, are you in the room? All right, stand up and be counted. So when I went to the mic and said that building a backbone is now easy, we know how to do that. Any idiot can build one. Prime example standing right here on the rostrum. Joel stood up and said that, no, it wasn't easy, and why don't you tell us how to build a backbone? So Joel, blame him for this. So I'm looking at this and I'm thinking, building a backbone is actually not that hard anymore. On the other hand, describing how to build an entire backbone in 30 minutes is also hard. So what I'm going to do is I'm going to give you the short presentation on how to build a backbone in 3 slides, and then we'll go into the AOL implementation of one such backbone. And in future NANOGs, I'll probably drill down more into the specifics of our backbone design. So if you look back at my presentation on NANOG 29 in Chicago in 2003, John Mitchell and myself gave a talk on how we converted OSPF to ISIS on the AOL backbone. So if you take all these presentations as one group, we will lay out from the very nuts and bolts how the backbone was designed and built. Unfortunately, due to the time restrictions, we can't really go into as much detail as I would like. So I will break it up into various presentations, and I will go into excruciating detail on some of them, including this one later. So anyway, 3-slide backbone review. Hire RFP engineers, people that write RFPs, talk to the vendor, say, oi, run me up a backbone. And the vendor SCs will do the backbone for you. This is not hyperbole. There are plenty of people who have built backbones using this exact same methodology. And as Heidi Hayden, one of the original guys at UUnit once said, when you want it bad, you get it bad. And most people want a backbone in the worst possible way. So that was slide 1. This is slide 2. This is slide 3. Unfortunately, most of our implementations have stuck at here and have not yet made it here. But we are working on that. So one of the reasons I commented to Joel was the fact that the good old days were not the good old days. The good old days were actually pretty horrible old days, and I will give you some examples. The UUnit architecture was called the FRITCH, a frame relay interim crutch. And when your backbone has the word crutch in it, that's not good. The reason we had to do that was we did not have enough packets per second forwarding on the Cisco routers at the time. So we had to use things like full mesh frame relay and DS3s so we could get routers that would talk directly to routers over the frame relay circuit and not have to transit routers because the routers could not support packets per second of the traffic volume at the time. 3-COM cards, another favorite of mine, 3-COM Ethernet cards with a 1500 byte MTU and 2 kilobytes of buffer. So essentially you could have one packet in buffer, and BGP tends to get very upset when you try to send an update and you drop half the packets. The iOS upgrades, another favorite of mine. We would call Cisco, there are several Cisco engineers, some of them whom I shall not call by name, but TLI is one of them, where we would call them up and start upgrading the backbone. And on a good day, we would probably get 2 or 3 code builds as we discovered new bugs as we rebooted the backbone. Okay, this doesn't work. And Tony's like, I think I know how to fix that. Try this build. Oh, that broke. Oh, I know how to fix that. Try this build. So up to 3 builds in a night. Routers that if they got a routing update, until they process the forwarding table, would not forward packets. DEC giga switches. The UUNet backbone for a substantial portion of its life, is Jason Schiller still here somewhere? Is it still true that half the backbone is built on WorldCom Protect side OC12s and OC48s? Yes. So because UUNet was blue money versus the consumer green money, the WorldCom engineering folks would give us circuits on the Protect side of OC12s. So at any given point, about 5 to 10% of the backbone would be down because the rings had gone into Protect and preempted the UUNet circuits. Richard Colella, somewhere here, this is the LS210s that took 40 minutes to boot. So that made code upgrades and small maintenance windows interesting because you didn't know if you had bollocksed up the procedure till 40 minutes into the main window. 4 ASX memory leaks, where a PNNI update would cause a small memory leak. So what would eventually happen is after about a month or so, the ASXs would run out of RAM, and then one ASX would reboot or a circuit would go down, causing a PNNI change, which would cause the router, the switch to run out of RAM, crash. That would cause PNNI to reroute, sending a cascade of updates through the network, triggering RAM failures in the rest of the backbone. And of course, our favorite Cisco TTM line cards, time to market. OC30s, actually Cisco's not the only one to blame. I remember Cascade BSTDX 9000s, which the HISI ports could really only do like about 30 megabits. And they sold us as 45 DS3 terminators. So none of these problems are really here anymore. You can go to a router with a good expectation that what the vendors say, for pure IP forwarding, that what they say will kind of work. So these are the horrible old days. We are in the good old days now. I mean, I don't know the last time I had an actual core router that ran out of packets per second. I mean, with ACLs and filters, of course, there's some of that, but fundamentally, the architecture is sound. You take a bunch of routers, you run the latest code on them, you connect them with OCX links, it just kind of works. The methodology for building backbones is fairly clear now. You have 2 routers up here and 2 routers down here, and you connect them in some fashion, and then voila, you have a backbone. So how did we build a backbone? How do we take all those implementation details and turn them into a backbone? So you remember my slide 3, the part about profit? Revenue has essentially stayed flat. Traffic volumes have grown. And this is true across pretty much any ISP that I've talked to. At some point, you have to start recovering the spend, your capital that you put into the network to sustain the volume of traffic growth. You have to start recovering that. And the way to start recovering that is to make the network more efficient, and I'll go into some more details about that later. The killer app is bandwidth. That is the key part. I was talking to some people over at Korea Telecom, and what they were saying is people really want bandwidth because what bandwidth does to them is not they're going to run like peer-to-peer all the time. The key part about bandwidth is that it reduces transactional latency. You want to see that BitTorrent show over a 34 or 50 megabits fiber to the house, you can download it faster than real time. You want that web page, you want to refresh it, you can refresh it immediately. So the transactional latency, because the key residual of humanity now is time. People will trade money for time. And bandwidth gives them that. It reduces your transactional latency. You have time. That is the killer app that drives the internet, not services. So we've been running with our backbones have been predicated on 50, 65% models. What we are trying to achieve now is revenue models, the margins on 10% or lower. People keep saying that IP packets are a commodity, and so what? They're commodity. It doesn't mean you can't make money if you're a commodity. For example, ExxonMobil reported one of the largest corporate profits in history, trading quote-unquote a commodity, oil, which has been a commodity for many, many tens of years. All that stuff means that the backbone must have minimum touch, and your OSS and network monitoring systems are competitive advantages. Everybody buys the same equipment. You go to like Cisco, you go to Juniper, you go to Foundry, you go to Cisco, you go to Juniper, and you say, give me a core router. What? Give me a core router. We will. You go to level 3, you go to Quest, you go to like Global Crossing and say, give me a bunch of Lambdas. You hook them up together. Pretty much modulo 5, 10 points, you get the same discounts across the hardware, you get the same discounts across line cards. So your COGS, your cost of goods sold, your capital spend on the network is pretty much the same across the board. There are minor cost basis differences, for example, if you own your fiber versus buying fiber, but the margins are about 2 to 3, 5, 10% on those services. So the COGS for any backbone is the same. So where will you get the competitive advantage to survive? The competitive advantage will be your provisioning, your OSS, your NMS. Real options, these are not the options that fueled the stock boom. There's the actual theory and science of real options. And I probably will not go into that because it's long. The key part here is that today, market uncertainty is high. So basically, what we want is experimentation on services that deliver value, built on an infrastructure that is simple and can support your basic requirements, and the basic requirements that we've distilled down to are supporting real-time voice. Because pretty much everything else above that works. If you can make voice work, everything will just fall out for free. So what the AOL backbone has been designed to do is provide a good service and let innovation happen at the edges. The AOL product people come up with 15, 16 different products every couple of quarters, and they roll them onto the backbone, they roll them onto the edges, and see which sticks. This is a theory of you throw enough pasta at the wall, one of the pasta strands will stick to the wall, and you know the pasta is done. So we try, Richard is here, I know, he has very much held the philosophy that we should not put anything in the backbone that we can do at the edges. So instead of spending capital on making the backbone look like a TDM network, trying to impose TDM semantics onto our packet backbones, the real capital spend should be put into making the applications more resilient. Because eventually, you can take the application, you can leverage the work you put into the application and leverage it across the entire internet. For example, I mean, my entire job is to make sure the fact that I'm not needed at the company, that the backbone runs without me, and if it makes business sense, that AOL can just turn the backbone off and just buy transit from, say, level 3 or UUNet or whoever is the transit provider du jour. And the applications still work, because in the end run, AOL is not here to give me a job. AOL is not here to make a cool backbone. AOL here is to return value to shareholders. And the way to return value to shareholders is to make sure that whatever services they offer and charge people run on the most cost-competitive platform possible. Currently, it is the ATDN backbone. Tomorrow, it may be somebody else. So for AOL's perspective, the holistic company spend should be better spent on making applications more resilient rather than imposing TDM semantics on a packet backbone. So that all being said, this is what the AOL backbone looks like. It provides AOL Time Warner facility interconnections, internet connectivity for Time Warner cable, data centers, and it's actually a fairly simple design. We'll go into that. Just because it's simple doesn't mean that there's no traffic on it. I don't know if you can see this properly. The green laser pointer, my friend Kat actually got it to me for some time ago, and I like it very much. This is actually an artifact of our London build, where we actually had a little bit of double counting going on before we took all the routers out of DNS. However, the actual backbone growth is right about 250G. This is single counted, and I've shown like variants of this slide earlier on. For example, my NANOG 26 presentation at Eugene showed at that point the backbone had gone up to like 80 gigs of traffic. And so in about 3 years, we've gone from 75 gigs to about 250 gigs of traffic. This is single counted, so this is not a marketing number. So since the backbone does not consume or generate traffic, any bit that goes in also goes out. So if you just count the bits coming into the backbone, you have an accurate idea of the traffic traversing the backbone. And currently it's about, at 95th percentile, 250 gig. So there's some volume to it. I'm not just talking about like a design network sitting in my lab that can talk all these fancy theories about real options on. This is actual real money being spent here. So this is what the traffic kind of looks like. The 50 gigabit of edge traffic actually is 250 gigabits of edge traffic. I was editing my slides and managed to bollocks that up. So these are things that cause that 250 gigs of traffic. This is the infrastructure that supports that traffic. So there's actual real cost basis to this. It's not a small network. These are the applications we run on it. 7.3 million active AIM users. These are stats as of like couple of weeks ago. All these people actually run every bit that goes over the entire AIM service goes over the backbone. So there's substantial amount of real users on it, and they become very irate, even though they're free, if there are any issues with the backbone. So now, every backbone is a financial issue. I mean, I know there are some people who build vanity backbones, but this is no longer 99. We no longer have enough capacity to throw around. So these are the AOL financial policy metrics. So OIBDA, cash-related expenditures, SG&A. These are how AOL breaks down the cost allocations. We don't set this policy. Our corporate financial folks set policy. We just design our backbone with regards to satisfying these policy decisions set by corporate. And of course, the end reason is the fact that it's hard to sell services when your switches are locked in non-conform cages across the world. So when we decided to go up and build the backbone, we decided to look at things of, can we just buy capacity from somebody else, like level 3, and how would that work over the long period of time versus going out, buying fiber, buying lambdas, buying routers, and then of course the associated SG&A to support all that infrastructure. So according to our policies in the previous slide, we basically run an NPV model, which we take the cash flow out and run it back to present time and see if it gives us a payback. And we weigh the cost of capital because cash loses value over time. So we weigh the cost of capital, put that into the model, run it back, and does it make payback within 18 to 24 months? And if it does, the financial people go ahead. And there's this little bit of fudge factor in there over the 24 periods of months, because there are some services that we can offer, control our own destiny. But mostly in the New World Order, we have to justify every bit of spend on the backbone, and these are the models that we use to justify the spend. So this is what the backbone looks like. It's a little bit out of date. There's an OC 768 STM 256 or 40 gigabit link now up between two of our data centers. I haven't turned that in here. And Europe looks slightly, there are more circuits there than it looks like. So it's a backbone, spans 4 continents, 10 gigabit backbone links. And more circuits are coming in, but I haven't shown them here. So, design philosophy. Susan, how are we doing on time? Okay, so I'll have to speed up. Please hold all questions till the end. The entire backbone is actually, I was making a dig at the RFP engineers, but the entire backbone is built, designed in-house because we have a philosophy: if you don't know how to run and design and operate it, and it's a core business requirement, you should probably find another job. So everything for the backbone is done in-house. The design criteria are, of course, the standard: no single points of failure, redundant capacity to support peak load, and the entire system is run on a routed topology for now. We do have things like MPLS enabled and ready to roll out, and in case we have also rolled out some some small services using LDP. But I will not go into that today because no time. And of course, what we do is every quarter we have a complete system review where we take our traffic matrix and impose it on our current topology, and then we fail various components. We fail links, nodes, routers, we fail data centers, and see how that traffic mapping occurs on the backbone to make sure that we have enough capacity to continue providing service. So the entire backbone is very standards-based. It's consistent, because one of the things we learned earlier was just because you're running an M7 versus a T640, the nodal architecture should remain the same. It's the same 4 boxes connected in a bow tie, and it just so happens to be Cisco 7206s in one POP and CRS1s in another POP. The reason for that is that if it looks consistent, it makes hiring new employees easier because there are no gotchas. There are no exceptions to the site because, oh, that site is different because Rajesh Bansal built that site 3 months ago and he had to do some optimizations, and he knows why this fiber is run that way or why this particular static route is sitting in the network. There's almost none of that. I mean, this is a real network, so there's modulo, there are like some local optimizations we have, but everything we've done is try to be behind the technological curve. We are not interested in this being a sexy, we're not interested in service, we're not interested in this being rocket science, because, well, we are not rocket scientists here, so it has to be simple so we can understand it. And what this allows us to do is automate the stuff and push it out into things like the NOC, which have a fairly high turnover rate. I don't know if there are any operators here with like large NOCs, but NOCs traditionally see some of the highest turnover rates of any single organization within a company, and outside of customer service, of course. So the things have to be simple, they have to look the same, because you push them into the NOC, and within a year, about 30% of your staff will leave, and you're spending a lot of time training new people and bringing them up to speed. So if it looks the same across the board, it's easier that way. So again, holding back to that philosophy, there's no rocket science in the network anywhere. The routing policy is based on very simple metrics. The entire focus of the backbone has been to reduce operational expenditure. Again, it's not about building a network that is cool, it's about building a network that works and is simple. So here's the logical design of the backbone. This is like one of our, there's another link coming across the country and 40 gigs here. I haven't shown. But the key part here is to watch this space, and I will go into that later. This is our European portion of the network. The color codes are different vendors that we use for our backbone. And you will notice that we try to go across different paths in the country using different vendors, so any particular single point of failure doesn't completely screw the connectivity up. The key part here is that we are starting to run out of paths across the country. And as we add more and more traffic, you get to the point where you either have to start doubling up capacity on these links, and then obviously you have to take that same capacity and then double it up across these links. So with the current 3-path situation and soon to be 4 paths, you can take any one circuit failure and you have 3 diverse vendor and physical paths across the nation. However, after the 4th path, things start to become harder. And these are 4 cost-effective paths. Of course, you could buy like exorbitant prices from AT&T, but we're not going to do that. So the cost basis of your network now doubles, because essentially what you're doing is you're buying bundled links. So the 5th path, say for example we buy a 5th path across the back country here, we will have to buy an equivalent path across the country here. So your cost basis for cross-country circuits just doubled, because now we are failing them over as bundles of 2. So instead of n+1 redundancy, now we have 3-to-1 or 2-to-1 redundancy. So this starts to look like a SONET BLSR ring. Again, the standard hub design, you have big routers up top that talk to the rest of the backbone, edge routers at the bottom. It's a 2-level hierarchy, edge and core, optimized for OpEx and SG&A. And currently, we are over-provisioning bandwidth, but as I spoke to this slide earlier, at some point, we'll have to start looking into traffic engineering techniques because of the fact that we are running out of viable paths to fail the backbone over. The key part here is that we have the edge and core, contrary to like what our vendors are trying to tell us, telling us one giant box that will replace the entire POP. The edge and core still, for now, want to do different things. So basically, we have an interface at the core, and then we have an interface at the edge. And depending on various business and technological imperatives, we can switch out the core and we can switch out the edge at different times as long as the interface presented remains the same. So we can replace technology depending on whatever imperative it is that makes sense at the time. So we can evolve the backbone in pieces. So as you looked at the logical design, the AOL core transit network consists of like a few large hubs. What this does is it reduces the number of transit paths in the network. There's only one of 3 ways you can go across the backbone. And so not being a large, dense network in terms of nodal density, it removes combinatorial paths. So you only have like 1 or 2 best ways to get across the backbone, and you either have them or you don't. So this makes the backbone fairly simple to traffic engineer. You raise the metric on this link, traffic will fall to one of the other 3. It's not like you raise the metric here, traffic goes here and then goes there and there. It's simple because we are simple people. Routing architecture. BGP, ISIS, we run the IGP extremely lean. There are like only a couple of hundred real the routes in ISIS, consisting mostly of our backbone links, some peering links, and loopbacks. And everything else is in iBGP, and I will get to that and how we did that. I explained the cost structure in excruciating detail in the NANOG presentation, but essentially we've broken it down to local, regional, long-haul, and international. Pretty much every ISP independently comes to the same conclusion because this is a cost-based metric assignment. You want to keep traffic local if possible and try to use wet fiber the least and long-haul slightly less, and then local you don't really care. So we take no protected rings at the SONET level. All we do is we take lambdas, because no matter how protected a ring is, eventually they will groom it onto the same conduit, they will groom it onto the same fiber, and then owned. So one thing we've noticed is that we have the matrix of city pair flows that tell us how our traffic goes. And macro flows, the law of large numbers, makes our flow tractable. We can pretty much predict day to day, week to week, how traffic will flow across the backbone. Traffic wants to go from the same places to the other same places on a fairly consistent basis. So this makes traffic engineering fairly simple because we have aggregated all our traffic. This is not to say that the traffic characteristics on a very small time scale are not fractal or heavy-tailed in general. What I'm saying is for our traffic planning purposes, the macro flows are tractable. And of course, the viscosity of bandwidth at the edge is extremely, extremely high. So the edge provisioning, anybody who's gotten a peering circuit from AT&T and knows I'm speaking truth here, it takes an amazing amount of time to turn up capacity with some of our peers. That is the constraining factor in backbone evolution. I'm actually running out of time here, so I'll just speed up. This is a standard policy. We actually, I know Paul Vixie, I don't know if he's here or not, but he and I used to have this discussion when I was MFN. AOL actually has done what he was trying to get us to do at MFN, is we've actually put full edge packet filtering. The key part here is packet filtering. Every packet that comes into the backbone of the edge is run through a filter. And the filter, of course, filters things like AOL infrastructure space as a source IP address, because no AOL infrastructure space should be coming into AOL as a source. And of course, we do RFC 1918 filtering, blah, blah. The peers, actually, this goes back to my first presentation I gave at NANOG. We still do coarse filtering at the edges for our peers. We use AS path filter, so not AS path filters, maximum prefix is used as a core sanity check for our peers. All our customers, the routes that we transit, are fully filtered on exact routes that they announce us. We have a large RDB that filters the customers. Thank you. So going back to the OpEx, AOL, for some reason, is a fairly large target for hacksaws. So we used to get like paged all the time because our routers were getting DDoSed. So we worked with our fine vendors. This also goes back to my NANOG Eugene presentation and other presentations I've done, where we need to harden the infrastructure. And so we have things, so finally we got things like receive ACLs and IP firewall filters. By the way, I'm using Cisco syntax because this is for compactness purposes. The Junipers have the exact same policies applied. They're just longer, so it's not like a bias against any particular vendor. We have both vendors in our backbone. We also have Foundry. Not in the backbone, though. So we put things like access lists in, and even though they're not perfect, because what I really want is this filtering to be done at the right after the framer on the line cards. This is good enough, quote unquote, for now, that we barely bother responding to DOS attacks in under a gigabit range now, because they're just background noise, and if we actually cared, we would be spending all our time working those issues. So these things have allowed us to actually take some of that SG&A we were spending on protecting our infrastructure away and put into better things, like, for example, giving talks at NANOG. This part is non-trivial. This is the reason I put it up, because when we did this filter, we completely forgot about BGP collision detection. So we put the filter in, TCP NE equal 179, all good. Turned it on, half our peers didn't come up. What happened? Oh, depending on how the BGP collision detection algorithm resolves, chances are pretty good about half the time your peer will have the source port of 179 and your destination as an ephemeral port, and half the time it'll be the other way around. So we had to put in the second line and so that we could get our peerings up. Important. And of course we have OSPF NE. This is only for routers inside the backbone. We deny packets coming into the backbone that have any OSPF in them from egress links. So, so this is how we put routes into BGP. The goals were minimal manual intervention, and it should be flexible. We don't want engineers to sit there, type in router BGP 1668, network blah, netmask blah, because they tend to fat finger those kind of things, and we've had some outages using OSPF where we managed to fat finger the net mask. So this is how we implemented our redistribution. We redistribute connected and redistribute static into BGP, into iBGP, using these route maps, and these route maps have certain policy that I'll go into in a second here. And the key part here is the fact that now any engineer can go to a backbone, turn up an interface, turn up a peer, turn up a statically routed customer without ever having to go into router BGP. This removes another potential point of failure while we get to the make it so button where all our configs are automatically generated. That is also a topic for another NANOG. So this is what it looks like, the route map. This is the standard stuff. This is connected. This was put in and is non-intuitive. This stanza takes care of public exchange points where we are, because you don't want to take those routes and give them to peers because they already are either connected to that exchange point or the exchange point is announcing those prefixes. But you do want to send them to the customers so they can do things like trace route through the exchange or trace route to the exchange. So what happens is we know that these are exchange point prefixes. They're put into this prefix list, and then we tag them with a separate community, 2xxx, so they don't go to peers, but they do go to customers, and then the standard, of course. The reason we also set origin IGP is that we know that where this route came from, and we set the local pref high because of the reasons of consistent announcements. If we set the local pref to the default, depending on where you are on the network, you may or may not announce that particular route to a peer at that exchange point or at that peering, causing inconsistent routing. So all said and done, how did we do? Traffic volume has grown about 230%. In about the same time, we have lost a bunch of engineers. So our SG&A has gone down while we've pretty much almost trebled our bits carried on the network. So overall, when I was talking about the scheme of optimizing for SG&A, optimizing for OpEx, we've so far managed to pull it off. So here's the cost per bit of major components. Normally, this is the fixed cost, and this is SG&A as an STM1. Normally, as your fixed cost basis goes down, and this is the thing all ISPs are familiar with, this is called margin squeeze. As this goes down, your SG&A tends to go up because as a percentage of making an STM1 worth of bandwidth, your SG&A remains fixed. You're still paying the 4 engineers or 6 engineers the same amount. It's just that the percentage of it goes up. AOL actually has managed to bring that down a little bit as opposed to just staying flat or in worst case going up. So I think we're doing pretty good on that. All said and done, we ran into, due to our redistribution into BGP, we ran into a fairly obscure condition. I see Richard is smiling. This is when we bollocksed Milan completely up. So this is Milan. We are actually making redundancy here, but at that time we did not. So this particular router has a peering on this interface, which is a large tier 1 ISP in the US. This router was the router under maintenance. So we took this particular router without turning the peering off on this router. What happened was, so if you look at it, you see that the peering interface, the 226 interface, is on Milan, and to get to Milan, you get the route in ISIS. So what happened was, we shut down the router in Zurich. We did not shut down the peering. The reachability for Milan in ISIS went away immediately because ISIS converged on the order of a second or so. And since we take our AOL space and nail it up on all our backbone routers, the next hop of all the prefixes, like 40,000 prefixes that were in Milan, were now reachable from every router locally. So this is what happened. IGP reachability from Milan goes away. iBGP has not timed out. The next hop is now local. So all the routers, I can get to all those prefixes by an internal cost of 0. What happened? BGP, I'm in your base, killing all your routes. And our pagers went insane because we lost, I don't know, like 40, 50, 60,000 subs just went away because we black holed the entire prefix list coming from that peer. Unfortunately, the problem was that now this particular prefix, set of prefixes were reachable with an IGP cost of 0 from all the routers. Any multi-home traffic, people who were quote-unquote multi-home by connecting to Tier 1A and Tier 1B were now also reachable via a shorter distance from Tier 1A. So people who were multi-home still got black-holed. So in fact, we black-holed more traffic than we were actually sending to that particular peer at the time, because we also took all the multi-home traffic and sent it to that particular peer as well. So lessons learned. This is how we mitigated it. In ISIS, we implemented a redistribute static route using this particular policy. And this is what the particular policy looks like. This is all AOL backbone loopback space. We take that policy, description, mitigate black holing when edge next hop dies without being withdrawn from iBGP. Yes. And we put this route. We took this and put it on 2 routers at the far sides of the network so that in case this happens again, the IGP is, for that particular backbone link, is still resolvable at a higher cost than the null 0. Oops. And that's it. We are done. Any questions?